So today we're going to talk about linear algebra over finite fields. And we're going to see many of the things that we have done over the real numbers and the complex numbers, how one does them over finite fields. And as for the problem one, which is due tonight, it's a problem on the polarization identity. The polarization identity is a really beautiful identity. And it tells you pretty much how to express the dot product in terms of lengths, in terms of the magnitudes, the norms of specific vectors. So what you need to do is really expand the right-hand side. That's all that you need to do. Let me give you an example. So how do I expand, for example, I times u plus iv, right? Let's do this one as an example. So the square of the norm is the dot product of the vector with itself. So this will be u plus iv, comma u plus iv, right? And now you can do your distributive law. So this will be I times u, I said u, I meant inner product, u inner product with u plus u inner product with iv. Make sure that you keep the order of things, iv comma u plus iv comma iv, right? And here the interesting thing is that when you factor out I from the first component, it comes out as simply as I. But when you do it from the second component of the inner product, it comes out as negative I. Why? Because the inner product is sesquilinear, meaning 1.5 linear. So this will be I times u inner product with u plus actually minus here I u comma v, and here it comes out as I v comma u, and here you will get one I and one negative I, and I times negative I is 1, so this will give you v comma v. And you have an I in front. And so this will become I times u inner product with u plus u comma v minus v comma u plus v comma v. Basically, I claim if you do the same thing for the other three norms that appear there, everything will cancel out, and you will get u comma v 4 times with the 1/4 that will eventually give you 0. Okay, so it's pretty much, this problem is, simply speaking, a problem of expanding what you have on the right-hand side. That's all. Okay, it's just algebra, and like I said, it's one of those singular problems where you don't expect to see anything like that on the final exam, but you know, it's just a one-time opportunity to see something of this type. Now I would like to go over to finite fields, but before I go to finite fields, I would like to just go over the arithmetic on finite fields. So in particular, let's go to F7 and do some operations. So how much is 3 plus 5? How much is 5 plus 6? How much is 3 times 3? How much is 4 times 6. How much is 6 times 6? How much is 5 plus 5? Let's do this. And then let's also find all the inverses. So let's find the inverse of 1, the inverse of 2, the inverse of 3, the inverse of 4, the inverse of 5, the inverse of 6. Let me remind you that when we talk about F7, we mean all the remainders upon division by 7. Those are 0, 1, 2 through 6. And when you add two of these things, what you really do is you either find something which is already between 0 or 6, or you take the remainder upon division by 7. So for example, if you do 4 plus 4, that's 8. 8 is not one of the remainders. So you replace 8 with its remainder upon division by 7, which is 1. So 4 plus 4 is 1 in F7. And as for the inverses, you find the number so that when you multiply it by the number whose inverse you try to compute, you get 1. And once you're done with those things, I would like you to also do the same thing for F11, just in terms of the inverses. So could you please find 1 to the negative 1, 2 to the negative 1, 3 to the negative 1, 4 to the negative 1, 5 to the negative 1, 6 to the negative 1, 7 to the negative 1, 8 to the negative 1, 9 to the negative 1, and 10 to the negative 1. The number 0 does not have a reciprocal. It doesn't have a reciprocal in real numbers. It doesn't have a reciprocal over this type of numbers. Okay? So please go ahead. I'll give you a couple of minutes and then we'll do it together. Okay, let's do it together. So 3 plus 5, let me try to do this in as much detail as possible. So 3 plus 5, that's 8, right? You always do it the regular way. And then you ask yourselves, is 8 a remainder? The answer is no. So replace it by its remainder. What's the remainder of 8 when you divide by 7? 8 is 7 times 1 plus 1. So that's 1. 5 plus 6, that's normally 11. What is the remainder of 11 when you divide by 7? 4. 3 times 3 is 9. What is the remainder of 9 when you divide by 7? 2. 4 times 6 is 24. What is the remainder of 24 when you divide by 7? 3. 6 times 6 is 36. What is the remainder of 36 when you divide by 7? That's 1. That's always true in any finite field. So in other words, let me just put this in general. In FP, always P minus 1 times P minus 1 is 1, always. Which means that P minus 1 is its own inverse. 5 plus 5 is 10. That's the same thing as 3. So we just said that the reciprocal of 1 is 1, and the reciprocal of 6 is 6. So these two things are for sure. So all you need to do is figure out the other reciprocals. The reciprocals come in pairs. So what is the reciprocal of 3? It has to be one of the numbers 5, 4, or 2. I mean, give it a try. 3 times 5 is 15. 15 is the same thing as 1. So the reciprocal of 3 is 5, the reciprocal of 5 is 3, and the other two need to be the reciprocals of each other. And of course they are, because 2 times 4 is 8, which is the same thing as 1. Questions, please. I mean, it does take a little bit of effort to get used to this new way of thinking, but once you get used to it, it's very, very simple, actually. Let's go to F11. How do we find the reciprocals in F11? I keep switching between reciprocals and inverses. You can call them either. So the inverse of 1 is 1. The inverse of 10 is 10. Okay, this is true for any finite field. The reciprocal of 1 is itself. The reciprocal of the last number is itself. And all the other numbers come in pairs. So for example, here there's a simple trick. Try to hit the numbers that are the same thing as 1 and try to factorize them. So for example, what is the same thing as 1? 12. 12, because 12 is 11 plus 1. So 12 is 3 times 4. So 3 times 4 is 1. So the reciprocal of 3 is 4. The reciprocal of 4 is 3. Also 12 is 2 times 6. So the reciprocal of 2 is 6. The reciprocal of 6 is 2. Then from the other ones, for 5, it has to be one of 7, 8, 9, right? If you do 5 times 9, that's 45. 45 is 4 times 11, 11 times 4 plus 1, right? So the reciprocal of 5 is 9, the reciprocal of 9 is 5, and of course 7 and 8 have to be reciprocals of each other because they're the only remaining ones. And of course, if you do it, you will realize that 7 times 8 is 56, 56 is 11 times 5 plus 1, so everything works perfectly as expected. Questions, please. Okay, so now let's do a little bit of linear algebra, right? Here's the great thing. We said before, no denominators. There's nothing to worry about here. So, for example, let's do one. Use Kramer's rule. To solve 2x plus 4y is equal to 1, 3x minus 2y is 5. And I have to specify what field I want you to work in. And to make sure that let's work in F11. In F11. Okay. Let me do this one for you. Let me show you how we're going to solve this. Okay. So we have our three determinants, right? D is equal to 2, 3, 4, and -2. Let's do this. How much is this? This is, so you first do it as if you were working over integer numbers, as if you were working over usual numbers. So 2 times -2 is -4, minus 12, that's -16. And now, how do you find what -16 is the same as? There's a good old trick that says, you know what, keep adding or subtracting 11 till you find the remainder. So here for -16, if I add 11, I go to -5. If I add 11 again, I go to 6. So that's the same thing as 6. Something tells me that this is not correct. So let's do it again. -16 plus 11 is -5. -5 plus 11, that's 6. No, it's perfectly fine. Sorry about this. Yeah. Okay, then let's find d sub x. What is d sub x? So you replace the column of coefficients of x with the constant. So 1, 5, 4, -2. So this will give you -2, -20. That's -22. -22, 22 is a multiple of 11, right? So it's the same thing as 0. So this is 0. And what is dy? Dy will be 2, 3, 1, and 5. So that's 10 minus 9. I'm sorry, 10 minus 3, which is 7. 7 is a perfectly acceptable remainder, so there's nothing to do with 7. Okay, so x, now this is going to be easy. If we don't, I mean, you could write 0/6, but what you really mean is that it's 0 times 6 to the -1. And it doesn't matter what 6 to the -1 is. We found it before, it was 2, right? So this is 0 times 2, which is 0. And how much is y? Y is going to be, how is -16 not 5? Let me come back to this again. I mean, or let me just answer it right away. -16 is the same thing as 11 times -2, which is -22 plus 6. The remainder is 6, not 5. Okay. And y will be 7/6, which is 7 times 6 to the -1, which is 7 times 2, which is 14. Well, 14 is not a good answer. We need to take its remainder, and that's going to be 3. So here it is. X is equal to 0, y is equal to 3. And if you plug them in, you will see that they satisfy your equation as it should. Okay? Questions, please. Let's compute the inverse of a matrix. Okay, just to show you how easy it becomes here. So let's take A to be, you know, put whatever you like. I mean, look at how, I don't care how I choose the numbers. The only problem is that I might end up with a singular matrix, but that's a completely different story. Look at this. I don't care. I mean, if I gave you, I would think twice before giving you this matrix over the real numbers, because it would produce big denominators. Nobody wants to work with big denominators. I don't want to work with them. I don't want to give you problems that produce such big denominators. But here, I'm saying we are in F7. We are in F7. Okay, so how do I find the inverse of this matrix, or at least see if it has an inverse, right? Find a to the negative 1 if it exists. If it exists. Okay. What is going to happen if the inverse doesn't exist? Can somebody tell us? How are we going to know that the inverse doesn't exist? What is going to go wrong in this process? We're going to get a row full of zeros, right? And the inverse won't exist. So look, 3, 2, 4, 5, 1, 6, 4, 5, 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. I mean, this math never gets more enjoyable than this. This is how good this is. Because look, I want to make this 3, the 3 that you see on the lower left corner, I want to make it pivotal. So I need to multiply by the reciprocal. What's the reciprocal of 3 in F7? Okay, we did it before. It's 5, right? So 3 times 5 is 15, which is the same thing as 1. So 5 times F1. And how much do I get? I will get 1. 5 times 2 is 10, which row 1. Why did I write F1? I don't know. Sorry about this. 5 times 2 is 10, which is the same thing as 3. 5 times 4 is 20, which is the same thing as 6. 5 times 1 is 5, 0, 0. See how nice it is? I told you it doesn't get much better than this. I mean, we will do this and you will start wondering, why didn't we work with finite fields all along? I mean, they're so much more convenient. Okay, let's eliminate now 5 and 4. So the opposite of 5 is what? So what do you add to 5 in order to get 7? The answer is 2, right? So you will do 2 row 1 plus row 2. And what do you add to 4 in order to get 7? In order to get 0, in other words, 3. So 3 row 1 plus row 3. Okay, so 1, 3, 6, 5, 0, 0. And then we have 2 times 1 is 2 plus 5 is 0. 7 is the same thing as 0. 2 times 3 is 6 plus 1, that's 7, that's 0. 2 times 6 is 12 plus 6, that's 18. And 18 is the same thing as 4, right? And here you will get 2 times 5 is 10. That's the same thing as 3, 1, 0. And then let's do 3 row 1 plus row 3. So here you will get a 0. 3 times 3 is 9 plus 5, that's 14. Oops, 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 oops. Do you see what is going on here? Do you see what is going on? You will never get a pivotal here. Okay. So once you're done with your first row, no pivotal on the second row. So we can stop right here. I'm sorry, on the second column. Not invertible. Yeah, that's it. Done. Okay. Questions? Because the whole process here is based on the fact that on the left you're going to get 1, 1. You're going to get the identity matrix, right? So once you're done with the first row, you will need a pivotal right here. by what we just said, since both of them are zeros, you will never be able to get a pivotal there. Okay, so I will finish the first row. I will finish with the first column by eliminating the first column, and then I will ask myself, okay, fine, let's go and eliminate now the second column. How do I eliminate the second column? I need a pivotal on the second column below the first row. Below the first row, I cannot use that 3, obviously. There's no such thing. Both things are 0. Okay. Because 2 is the opposite of 5. 2 is the opposite of 5. I'm sorry, of this 5. And 3 is the opposite of 4. I mean, normally, wouldn't we have said -5 row 1 plus row 2? Yes, but what is -5? What is the number that you add to 5 in order to get 0? 2. 2 was the opposite of 4? No, we are in F7. 2 plus 4 is not 0. 2 plus 4 is 6. Okay. 2 plus 5 is 0. 2 plus 4 is 6, and 6 is non-zero. Okay. Like I said, it does get a little bit of getting used to. Now, yes, the remainders after computing. And if you get something which is already a remainder, then you don't have to do anything. But if you get something which is greater, which is outside the range of the remainders, then you replace it by the remainder. Okay. Why don't we take a break, and we'll do more arithmetic on finite fields when we come back. Okay, so welcome back, everyone. Let's see if we have any questions. And actually, let's take a quick look at our homework for the last homework assignment, which is due on Wednesday, to see if there's something else that I'm asking you to do. And then I would like us to discuss what are the things, is it true that everything that we have done so far carries over to finite fields? We're going to find out that the answer to this question is no. And let's see if we can understand why. But let's see what I'm asking you to do for Wednesday. So basically, I'm asking you to find an inverse and to solve a system, which is precisely what we have done so far. Problem number 1 is asking you to solve an equation. Of course, you might say, how do we solve equations in F3? But here's why this problem is so easy, right? Because in F3 has just 3 elements, 0, 1, and 2. So all you need to do is just plug them into your equation and see if any of these numbers satisfies this equation. So in some sense, for some such small fields, it's a trivial matter to try to solve such equations. Okay. Does anybody have any questions on the homework problems? Again, please go to Blackboard and look at the last homework set at homework set number 13. I'm sorry, 15.
Professor, I have a question.
Yes.
I actually asked it in the chat, but I'm still confused about the reciprocals. In the example you have written over here, you're trying to get, for example, you have 3, 2, 4, 1. You do 5 because 5 is the reciprocal of 3. So
Absolutely.
then that makes sense. So then why are you doing 2 row 1 plus row 2? Shouldn't it be 3 row 1 plus row 2 at this point? Because the reciprocal of 5 is 3 and of 3 is 5.
Yes, but here you don't play with the reciprocal. You play with the opposite, meaning if for example, all of a sudden somebody told you you had real numbers here, what would you do? You would do -5 times row 1 plus row 2, right? That's the normal thing that you would do. So
Yeah.
then what you need to ask yourself is, what's -5? -5 is the same thing as 2. -5 in F7 is the same thing as 2. Okay.
Okay. All right. That makes sense.
Plus, if you try to actually do what you suggested, which is do 3, because 3 is the reciprocal of 5, then you would do 3 times 1 is 3, plus 5, that's 8, which is 1. We don't want to get 1, we want to get 0.
Okay. I get it
Okay?
now. Okay. Thank you.
Excellent. So why don't we try to understand, out of all the linear algebra that we did this semester, what are the things that are applicable to finite fields? Or in particular, is there anything that we have done so far which is not applicable to finite fields? Is there anything which, from everything that we have done so far, that would not sit well with finite fields? There's one thing and everything that comes with it, and that is inner product. Why? What's wrong with finite fields? The problem is that there is no order in finite fields. There is no order compatible with the operations. So you cannot really say what is positive and what is negative. And once this is true, that means that pretty much everything that we had said, because one of the premises, one of the reasons why the inner product was working was because the inner product of a vector by itself was positive. There's no such thing in finite fields. So the whole inner product and Gram-Schmidt method, all of those things are out of the window. Okay. And this means that we cannot have the same guarantees for the existence of eigenvalues that we had in the complex numbers. One might ask, do we have something similar to the fundamental theorem of algebra for finite fields? It turns out that there is a transition from a finite field to another larger field similar to going from R to C. The problem is that that other field, which is called the algebraic closure of FP, is infinite. It is infinite. It's an infinite field. So pretty much we lose the finiteness by trying to get something where all eigenvalues will exist, where everything is going to be similar to a triangular matrix. However, it is possible to do it. It is possible to do it. And there are a few things that are actually more convenient than working with R, but still, the moment you leave behind just something which is finite and you go to something that is infinite, there are always all sorts of issues. At this point, I would like to give you an idea of why finite fields became so indispensable in modern applications, and the linear algebra of finite fields as we saw it today. So here's the reason why. So first of all, we have to get a grasp on what is possible and what is impossible regarding big numbers. So let me ask you the following question, okay, just to see if we can get an idea of some limitations or the speed by which some things can be done. So let's say that I wanted, if I ask you to write down a number that has 100 digits, how long do you think it would take to do so? So I'm asking, okay, write down a number that has 100 digits. How long will it take you to do so? Yeah, there is a way to make I an acceptable remainder. You have to go outside the system that you have. So there is a process of constructing the so-called field extensions. So literally speaking, if the equation, so for example, for F3, you will see that the equation x squared plus 1 does not have a solution. So you could literally introduce an I here. But this is part of some less general process. Unfortunately, once you do that and you consider something which is known as F3 of I, you will realize that there are still equations in that field that don't have solutions, which means that you need to extend it further. And that's the problem. You keep extending it more and more and more. Eventually, you end up with a finite field, with an infinite field. But let me go back to what I was discussing a moment ago, which is how long do you think it would take you if I ask you to write down a number that has 100 digits? Actually, why don't we do this for our attendance so as to find out? So I want each one of you to send me a number that has 100 digits for your attendance. Okay, go ahead. No. I don't want abbreviations. And 10 to the, I don't want abbreviations. Pi doesn't have 100 digits. Please don't take shortcuts. You need to give me 100 digits. Okay, if you want to give me one with 99 zeros, fine, but write it down. Okay, as such. And pi is not an integer number, so it doesn't even qualify as part of a possible answer. So I want you to write down a number. There you go. Okay, that's what I mean. Okay, to type it, it takes you, a few seconds. All you need to do is keep track of the digits, right? All you need is keep track of the digits. Oops, what is that? In a message, that number didn't have 100 digits. It had like 20 of them. So if you have to type it, you see it takes a few seconds. If you have to write it by hand, it takes, the funny thing is if somebody was not following what was going on, now they have no clue what I'm asking you to do, right? Okay, that's not funny. I mean, it's sad, but in any case, you see some people are giving me, something completely different from what I want because they didn't hear what had been asked. But in any case, let me ask you the following question now. Okay, so let's leave now numbers that can be written by hand. And let's ask ourselves, if you had a computer, right? How long do you think it would take a very fast computer to produce a document that has all the numbers that have 100 digits? Okay, so again, here's my question. How long do you think it would take a very fast computer to produce a document, I don't know, a Word document or a text document, anything you like, that has all the numbers that have 100 digits. How long do you think it would take a computer to do that? It would give an error. What do you mean by it would give an error? It's impossible to write a program that produces all the numbers that have 100 digits. 10 to the 100 units of time. So how, okay, can you tell me in human time what that means? Oh boy, again, you're giving me all sorts of nice things. But honestly, when somebody asks you how long does it take you to do this, do you say 50 million seconds or something like that? That's why I'm telling you, give it to me in a way that I can understand it, right? Nobody talks like this. Nobody says, nobody talks in seconds, right? We talk in minutes, in hours, whatever. 0.0001 milliseconds. That's how long you think it will take to prepare a document that has all numbers that have 100 digits. Okay, good. I mean, look, here's the essence. Not only will it theoretically take billions of, more than billions of years, but the matter in the known universe, the matter, no, you don't use O notation like that. Don't, that's not how O notation is used. Be careful. You need to put variables in there. But in the matter in all of known universe is not enough, and there's not enough electrons, if you like. There are more numbers with 100 digits than electrons in the known universe. So not only would it take too long to construct something like that, you wouldn't never find the physical resources to actually have something like that. So the answer is it's impossible. That's why what you said in the beginning, it would turn an error. Basically, it would not turn an error. It would start. It would never end. That's how computers behave. You give them something that takes too long, the computer will start doing it. The computer doesn't know what it's going to take too long or a reasonable amount of time, right? So the computer will keep going. So the bottom line is that this is something which is impossible. And why did I bring this over out of the blue? Because there's a wonderful fact about finite fields. In every finite field, there exists u such that the numbers u to the first, u to the second, all the way to u to the p minus 1 are precisely the numbers 1, 2, all the way to p minus 1. So in other words, there is a basis for logarithms. That's what I'm saying. There is a basis for logarithms in finite fields. But here's the interesting thing. If somebody gives you a number and they ask you to exponentiate it, so imagine that you have a large P. When I say large P, let's say that it has about 100 digits. Hence, everything that we were discussing a moment ago. So imagine that you have a very large prime number. And now imagine that that somebody tells you to compute u to a big power, u to some n. and a large number. This is something that can be done very easily using computers. But now take the inverse problem, which is, imagine that somebody asks you to compute the exponent to which you need to raise your number in order to get n. So u to what power is going to give you n? It turns out that this is a problem that nobody knows how to solve within a reasonable amount of time. So it's one of those problems that the one way of the problem is doable, without too much effort. The opposite way is simply not doable in simple terms, in any simple amount of time. I mean, theoretically, yes, you could try all the exponents and see what works. But that's the reason I asked you to tell me what it would amount to trying all these exponents. And you can see you cannot even put the exponents in a file. You cannot write these exponents down, let alone try them all. So the one direction of the problem is perfectly doable. The other is far from ever being solvable. How do people take advantage of this situation here? Every time you have a mathematical problem with two directions, where one direction is straightforward and the other is practically impossible, not theoretically impossible, practically impossible, then you can try to take advantage of that and generate a system of encrypting information. Okay, and here's one of the classical setups in this theory. So imagine that you have Alice and Bob. Alice and Bob. These are actually the names that have been used in the development of the theory of cryptography. So imagine that you have Alice and Bob. Okay, so Alice and Bob have chosen a secret key in FP, where P is a really large number that has, let's say, 100 prime number that has a digit. So this is their secret key, a secret key. And here's Bob's secret key. So nobody knows what Alice has chosen. Nobody knows what Bob has chosen, right? The question is how the two of them can, in very simple terms, generate a key that will allow them to encrypt their communication, a key that nobody else can figure out, only the two of them. So here's what they do. They take that basis that I told you about before and they raise u to that number a, and this is uppercase A, and this is called the public key, and they publish this. Everybody knows that. If you actually Google public key and put a big company, you will see what the public key of that company is. So I'm not talking here about something which is, just in my mind. It's just that what I'm describing here is oversimplified. In general, this is much more sophisticated than the very simple approach that I described to you here. But here's the bottom line. The bottom line is that you can know what uppercase A is, but you don't necessarily know what little a was, because remember, there are no good methods to figure out little a. So what do we do then now? We ask, so how Alice and Bob will come up with a common number that nobody else can come up with. Here's what happens. Alice takes Bob's public key and raises it to the a power, the little a. Nobody can do this except for Alice, right? Because nobody knows little a, right? And Bob takes Alice's public key, which is a, and raises it to his secret key, which is B. Nobody can do this except for Bob, because it has the little b in it, and B is Bob's secret key. Nobody else knows it, right? But here's the little miracle that happens here. This is u to the b, all raised to the a power. And this is u to the a all raised to the b power. And those two things are the same. Algebraically, they're the same. So Bob and Alice have arrived at the same number that now can be their secret key for their communications. Nobody else knows that number, and now they can freely communicate. And this is just one instance of a mathematical problem, which is very straightforward in one direction and practically impossible in the opposite direction. There are other problems, such as take two large prime numbers, let's say each one has 100 digits, and multiply them together. Okay, and you find their product, right? I mean, you can do that. You can even do that over the internet if you like. Now, give that number to anybody you like. I don't care how smart they are. I don't care what computers they have. And tell them that, you know what, this number is the product of two prime numbers. Find those prime numbers. The bottom line is nobody can find it in any reasonable amount of time. So this is another type of problem. And, you know, both of the problems that I gave you here that are easy in one direction and impossible in the other direction are very, very, if you like, primitive problems. In general, people use much more sophisticated problems than this, and they make it pretty much impossible to break security from in a direct way. That's why nowadays, the only way that hackers try to break security is through social engineering methods, phishing, and so on and so forth. That's how they try to do it. And I should say here that exactly because the arithmetic of finite fields, it's so intimately connected with cryptography, you will find out that research for finite field theory is not just carried out by universities, right? But companies like Microsoft and Google and so on have their own mathematical departments that literally do research on this kind of fields. So, in other words, every time you send a text message, every time you send an email, every time you do any kind of communication which is considered to be secure, finite fields are at play. And that's why, in some sense, even though linear algebra is a fundamental field of mathematics that has a big amount of applications, an unlimited amount of applications, I should say, it is true that finite fields is pretty much that part that for which those applications become very, very relevant, very, very important. Okay, and with this, we're actually completing our material for this semester. We're going to look at some further applications, and then obviously we're going to focus on preparing for our exam. The exam is going to consist of 20 problems. Many of these problems were included already in the first exam. And most problems are very quick. For most of these problems, you will have to spend 1, 2, 3 minutes. But obviously, you will need to know them very, very well. As I said, if anybody has any questions regarding their current grade, please see me during my office hours so that we can discuss it in detail. And please do your last homework assignment for Wednesday. Of course, you have today's homework assignment. As usual, make sure that you submit it in the right place. And the final exam will be 2 hours long. And on Wednesday, we will have our last quiz. Yeah, we said in the very beginning that we would have 15 homework assignments, 15 quizzes. We have already seen 14 homework assignments and 14 quizzes. So have one more of each to go. Okay. The whole class is online. I'm not even allowed to give you an in-person final exam, because there are some of you who could be outside the country right now. Review plus other things that plus we're going to look at some applications. Okay, but I'm going to take attendance as usual for all these, all the remaining lectures. Okay, so there are 4 of them. Yeah, our semester is close to over, but I would like you to take this opportunity and try to prepare yourselves as well as possible. Okay, if your plan is to start reviewing after the weekend or on Wednesday, next Wednesday or something like that, it's not going to work. It's not going to work. Please start working right away. Okay, please look at those 20 problems, know which problems are the ones that you can do faster. Start with those problems, go to the other problems once you have done the ones that you can do faster. Okay, and again, I'm clarifying this because some people were a little unclear on the midterm exam regarding the duration. It's going to be 2 hours. Okay, does anybody have any more questions? I have my office hours in 15 minutes. So yeah, of course we did attendance today. Oops, you missed it. Sorry about this. So we will, I will see you on Wednesday. Be well and have a great rest of your day.